All right, so in the previous lecture we discussed, amongst other things, some of the mathematical properties of the Lorentz transformation. So we saw in particular how we could regard this Lorentz matrix taken from one coordinate system to the other as an orthogonal matrix. And one of the consequences of this was that it would preserve the norm of this position vector in Minkowski space. So actually one of the first things that we proved when we started on this topic was that this product of the two four-position vectors is actually an invariant under Lorentz transformation. So this is a Lorentz invariant quantity, and we also just recapped briefly some of the useful mathematical properties of orthogonal matrices. And in particular, we derived the following relation which should hold for the Lorentz matrix. You know, that the 4-4 element squared has to be larger than or equal to 1. And we mentioned that this could actually be used as a consistency check if you were asked, for instance, to find the Lorentz transformation matrix for some particular example. Then, unless this is satisfied, something might be wrong. And we also introduced these concepts of covariant and contravariant vectors in the context of metric. So we discussed a bit concerning different choices of metric. Now we've used the Minkowski metric, in which case x4 is ICT. But there are other choices which work just as well. But in that case, we have to change the so-called metric tensor. So we discussed this a bit the previous time. And we had just got started on the so-called covariant 4D formulation. And the usage of the word covariant in this context is a bit unfortunate, because it has nothing to do with covariant and contravariant vectors. So perhaps a better word to use is Lorentz invariant formulation. And this actually traces back to the original two postulates of the special theory of relativity. So the first one was that the laws of physics should be the same in all inertial systems. And the second one was that the speed of light should be a constant in all inertial systems. Have the same value in all inertial systems. So this covariance of the laws of physics, or the Lorentz invariance, is the mathematical formulation of this principle that all laws of physics should be the same, or have the same form, in all inertial systems. Now, any sort of law of physics we should be able to express as an equation involving scalars, vectors, or matrices. And scalars and vectors are just special cases of matrices. So in general, we should have the following generic form for some kind of law of physics. So these are two matrices now, written in component form. So what the Lorentz invariance of the laws of physics basically means mathematically is that if we Lorentz transform both sides of this equation to a primed reference system, moving with a constant velocity v relative to the original stationary system, we should have the same form for the equation. Now, what we ended the previous lecture with was the following. We wrote this. We know from before that the product of these two infinitesimal increments of the position 4 vector is a Lorentz invariant. We proved explicitly that it has the same value in any inertial system. And so we define now this value as minus c squared, where c is the velocity of light, and tau here is defined as the eigentime. And so one may pose the question, why is this called an eigentime? Well, consider the following scenario. It's basically our standard setup. We are here in the stationary system. And now we're considering a particle here, moving with a velocity v relative us. And now imagine that we're attaching a reference system to this particle. So imagine we have some observer sitting on this particle along for the ride. So from the viewpoint of the observer situated on this particle, the particle is at rest. Time, however, is ticking. So the increment in the 4-position vector, as seen from the guy sitting here, should be this. And if we now take the scalar product of 2 of these infinitesimal increments, we get this. And using then our definition here, we can identify immediately the following relation. So in other words, we now have more of a physical grasp of what this eigentime means, namely the following. So the eigentime tau is the time measured by a clock moving with the particle. So you can think of it as the intrinsic time an observer, which is sitting along for the ride, measures. Now, we know that this product here, oh sorry, I'm missing a prime here. This product here is a Lorentz invariant, meaning it should have the same value in the reference system of the particle as in our system. So let's now try to evaluate this product in our system. So from our viewpoint, if we were positioned in S, the particle is moving with a velocity v. So the increment of the position 4 vector describing this particle now has non-zero entries for the spatial dimensions, because the particle is now moving. All right, so like so. And keep in mind now that we're using a metric where the covariant and contravariant vectors are not distinguishable. And this is because the metric tensor is identity in our case. So in general, you would have to be careful about performing such a summation to make it Lorentz invariant, because you would have to take into account the metric tensor. But in our case, we can just forget about this because we're using an identity matrix for the metric tensor. Okay. We know that the velocity of the particle should be the following. Sorry, like this. Where I've now used the fact that this has the same value in all coordinate systems. So I'm using the definition here, and then I'm dividing the entire expression, both sides, on dt squared. So I get this, and here I get the velocity squared minus c squared. I can just rearrange this equation to isolate the increment in the eigentime expressed through the increment in the time measured from the stationary system and the velocity of the particle, like this. And so we get the following relation between the time that we measure and the time that an observer tagging along with the particle measures, the eigentime. Namely, they're proportional by this gamma factor that we've introduced previously. This one. And beta, as usual also, is the ratio between the velocity of the particle and us. So this has a very interesting consequence, because it means that the time that we measure, dt, is always greater or equal to the time measured by an observer tagging along with the particle. So it means that time actually appears to run slower for us than for someone on the particle. And this is known as time dilation. So a clock in S shows the time dt, which is greater than the time d tau, shown by a clock in S prime. Now, this is not the only bizarre consequence, if you will, which occurs when you have moving inertial systems or moving reference systems that have speeds comparable to the speed of light. In fact, there's one more interesting phenomenon. Consider now the following situation. We are, again, in S, the stationary system. And now S prime is a reference system which is moving relative to us. And in S prime, imagine that there is some object. So to make this a bit more, to visualize this, say you're on a platform and say that this is a train. S prime is attached to a train which is moving. And on this train is some object, for instance, a ruler. The ruler has a length L0 as measured in the train. So if you're on the train and you measure this ruler, then you will find the length L0. So the question is now, what length do we see as observers in S? Will we see the same length or a different length? So this S prime is moving with velocity v compared to us. And we know how to go from the coordinates in S to S prime. We do this via a Lorentz transformation. And I've just put the relative motion along the z-axis here, but this is no real loss of generality. So we have the following relation. Now, we assume that the measurement of this object is done at equal times. This should be reasonable. So the difference between these 2 points we should be able to write like this. But now, we use that the time at which we perform the measurement is the same. So in other words, we're measuring the position here and the position here at the same time. It's an instantaneous measurement. In that case, this term cancels. And so we obtain the following relation, namely that the length as measured in the system where the object is at rest is proportional to the length as seen from our system, again with a proportionality factor of gamma. And we see that L0 here will always be greater than or equal to L. So this is, in a sense, opposite to the time case. Because here, the time measured by us in the stationary system would always be greater than or equal to the time measured in the moving system. But here, the length in the moving system is greater than or equal to the length in our system. So in other words, we have the phenomenon of length contraction. And what it means that moving objects actually appear smaller than if they were at rest. So both of these phenomena, time dilation and length contraction, we have now derived using the invariance, the Lorentz invariance of this product here. But this has to be a Lorentz invariant quantity. And so they follow directly from this. Now, to see how this works in practice, we'll have a look at a couple of examples. So we'll have a look at a lifetime for a particle known as a mu meson. And the situation we're considering looks like this. In fact, this is a poor word. Let's just use muons. Sorry about that. So it's something like this. We have Earth, and then we have this muon particle, which typically is produced in the upper atmosphere as a byproduct of cosmic ray collisions with the atmosphere of Earth. And so this particle is positioned initially at distance d from Earth, and it has a velocity v coming towards Earth. And here are some facts about the muon. Its lifetime before it disintegrates, as seen, as measured from the rest system of the muon. So if you're an observer tagging along with the muon, you would measure a lifetime of 2 microseconds. So these are really fast particles. Their velocity relative Earth is pretty close to the speed of light. It's 2.994 approximately times 10 raised to the power of 8 meters per second. Okay, so taking into account the lifetime of the muon and its velocity, we should be able to calculate how far this muon travels before it disintegrates. $600 meters. All right. Well, at least this is the non-relativistic result. Very well, so we found the distance the muons should travel, and since they're produced typically at a distance d of order 6 kilometers from the surface of Earth, it means that we shouldn't detect any muons because they should die far earlier than they would reach Earth. So the problem with this is that experimentally, muons are in fact detected in an abundance at the surface of Earth, in spite of the fact that the distance traveled by them, or the apparent distance traveled by them, I should say, is smaller than the distance at which they are produced. And as you may suspect, the key here is that we have to treat this problem relativistically, precisely because of this very high velocity of the muons, which is comparable to the speed of light. So the resolution to this apparent enigma is by considering a relativistic calculation, and there are in fact two ways or two viewpoints we can take. One possibility is to take the viewpoint of the muon. Yeah. So the question is, what is happening here as seen from the reference system attached to the muon? Imagine you're sitting on this muon and you're speeding towards Earth at an incredible velocity. What would you perceive? What would your lifetime be? you're in the rest system of the muon, so your lifetime is 2 microseconds. So then the question is, what is the distance to Earth that you see?
Gamma times d.
Gamma times d. Okay. So let's see here first. We have lifetime tau, and then observed distance. Gamma times d. Okay, so gamma should be pretty large, at least larger than 1, because we have velocity comparable to the speed of light. And d is 6 kilometers. So then the observed distance should be greater than 6 kilometers. Does this seem okay? No. Because if it's greater than 6 kilometers, then we're at an even worse position than before. Then we would for sure not reach the surface of Earth, right? So would you like to modify your answer?
Divided by gamma.
Divided by gamma. So let's see how this is obtained. So again, the fundamental equation that we can use here is just a Lorentz transformation, which we can choose again to be along the z-axis. And it gives us the relation between the difference between the distance z prime, as seen from the muon system, and as observed from Earth, and the distance z and time t, as seen from the muon's rest system. So keep in mind that from the point of view of the muon, Earth is approaching us with a velocity v. And according to this phenomenon of length contraction, we know that moving objects should appear smaller. So the distance to Earth, as seen from the muon, is the distance as seen from Earth divided on this gamma factor, which equals 375 meters. And this is because Earth is moving towards the muon at a very large speed compared to the speed of light. And so the length here is contracted as seen from the muon. So if the distance to Earth is 375 meters, and its lifetime is 2 microseconds, well then, this is below the threshold of 600 meters, right? So according to the muon, it should reach Earth, but only because relativistically you have to take into account the length contraction. So put differently, Earth reaches this muon at a time z over v, which is about 1.25 microseconds, in effect before the muon dies. So this is one perspective. This is as seen from the muon. Now, we should be able to reach exactly the same conclusion if we take the viewpoint of an observer at Earth. So let's try to do that. In this case, there is no question about the distance. The distance to the muon, where it's produced, is 6 kilometers. But now the question is, what happens with the lifetime of the muon as seen from Earth? Now, the muon lifetime is in fact increased due to this time dilation phenomenon. Namely, moving clocks appear to run slower. So the clock in the muon system appears to run slower than our clock. So the time that we measure is greater, is longer. So this gamma factor is about 16, I think, yeah, for that velocity. So the muon's lifetime as seen from us is enhanced by a factor of 16. So with this new lifetime of the muon, a typical muon may travel a distance equal to the velocity multiplied with this lifetime, which now is equal to 9.6 kilometers, which is greater than d, 6 kilometers. So in effect, most muons should reach the surface of Earth. So I wanted to, I wanted to give you both perspectives, both as seen from the muon and as seen from Earth, to see that we reach the same conclusion, but we have to take into account different effects. As seen from the muon, the lifetime is set. We have a clock, we're measuring how long we live. But the distance as seen to Earth is length contracted, because Earth appears to be moving towards us. As seen from Earth, the distance to the production point of the muon is fixed, but the lifetime of the muon is different than the eigentime of the muon. So by taking into account length contraction and time dilation, we can understand why muons reach the surface of Earth. There's a famous paradox related to the special theory of relativity, which is known as the twin paradox. And we'll just have a very brief look at it. And the scenario that one may envision is the following. Say we have two twins positioned here at some platform in outer space. So it's a highly realistic scenario. Now, each of these twins have their own spaceship. One of the twins, twin B, takes off into space with a velocity v. Now, at some point, he turns around and comes back, eventually returning to twin A. So these twins are now reunited. The problem here is that if we are twin A, standing on the platform and waiting patiently for our twin B to return, let's say we would measure time t for the time that he has been gone. However, a clock in B would predict that this time should be equal to t over gamma. So B would expect that A should measure a time t over gamma on his clock. Now, when the twins are reunited, they open the doors to their spaceships and look at each other. And the question is, what do they see? Because according to one clock, one should be older, whereas according to the other clock, the other should be older. And I'll leave you with this dilemma for the break, and we'll return to it afterwards.